Hi, Assalamualaikum and a very good evening from Malaysia. So on behalf of the project-based learning team, which comprise of students from both University Science Malaysia and Silesian University Technology Poland, I, Putrino Atika, will present the output of our PBL. So it is a project supervised personally and closely by the GeoDRR team leader, Professor Christoph, which entitled Numerical Study of the Influence of Water Saturation of a Soil and or Rock Medium on the Possibility of Landslide in the context of different geometrical and material properties of this medium. It is a case study of the 2022 Batang Kali landslide in Malaysia. So this is the overall table of content for my presentation today. So, in the context of landslides and mudslides event, the main identified triggering factor for such event in the Southeast Asia region is heavy rainfall. So, the map on your left-hand side is a landslide susceptibility map overlaid by the reported landslide fatalities, which was provided by the NASA organization and are freely available to be downloaded. Um, so, um, According to the map, the Southeast Asia region was identified as hotspot for a landslide event during the monsoon season. As you can see, the percentage for the frequency of forecasted landslide is high during the monsoon season, which is between June to August. And the number of reported landslide fatalities increases following the monsoon season as well. So it is a well-known fact that soil saturated with excessive water, together with another factors such as human activities and design errors, lead to slope instability. Because heavy rainfall is considered as main triggering factor, hence water is essential in assessing a slope stability. Why? Because the presence of water increases active lateral pressure of the slope, in which it decreases metric suction of the soil medium and reduces its shear strength. So in slope stability analysis, particularly the Mohr-Coulomb model, tension, cohesion, and internal friction angle is an important value. So this graph shows you the relationship between a soil's water content and the value of cohesion and internal friction angle. So in which we can see that the value for both decreases significantly with an increase of water content. So meaning that the water saturation causes a sharp decrease in strength properties and increases in deformability. So for these figures, it shows a slightly stable slope in which in the case of lowering the groundwater level, we can improve the slope stability and reduces the probability of a landslide. So this is confirmed by the results of soil and rock strength tests in previous study. Infiltrated rainwater or water content in the soil actually behaves like a softening agent or lubricant for the sliding surface. Hence explains why water is key in slope stability analysis and improvement. There are several different approaches in slope stability analysis, in which the earliest technique developed is the limit equilibrium method. So it is a simple and accurate method where the assessed slope is cut into fine slices and equilibrium equations are applied to each slide. So the limitation in this method is it could not simulate a complex slope. But with computer advancement, slopes with complex mechanisms are able to be simulated through the numerical modeling method, where this method able to simulate slopes with very high realisms and provides better visualization for the soil deformation. So the usual technique used under this method is the shear strength reduction modeling, where some criterion are being reduced in each iteration until failure occurs. Finite difference model and finite element models are the usual method used under the numerical modeling, and The third approach is the artificial neural network. So ANN is a good modeling technique for understanding a complex system. However, it has some limitation as it couldn't perform reliable estimation outside its range of training parameters, and it requires the modelers to have a high understanding of the real world problem. Before we dive deep into this research, I'll give a snippet of information of the 2022 Batangkali landslide disaster. It occurs in December 2022, displaced about 450,000 meter cube of soil, and this is the aerial view of the tragedy and some pictures of the tragedy obtained from Malaysian newspaper. So the landslide killed 31 people. So this is the campers who spent the night at the nearby campsite, and 8 people were hospitalized and about 61 people were rescued under the rubble. So this tragedy was recorded as Malaysia's second worst landslide just after the Highland Tower tragedy back in 1993. The objective of our research is to numerically investigate the influence of water saturation of a soil medium on the possibility of landslide occurrence in the context of different geometrical and material properties of the soil medium. So we are taking the 2022 Batangkali landslide event as our case study, and to achieve this objective, we are using the FLAG 8.1 software to simulate the slope failure under water saturated condition. This is our study area. So the Batangkali landslide area is located in the Selangor state of Peninsula Malaysia. So this is the video post tragedy showing the site of the beginning of slide, in which it reveals the shape of the sliding surface. So this video actually helps us so much in developing the slope geometry model, because we don't have any on-site data and we have to do everything using data available online. So this is the rainfall sum average for 2022 in Batangkali. So you can see that the event occurred during the month that the site receives the highest rainfall, which is December, approximately 500 millimeter. This emphasizes the effect of water saturated conditions during the landslide event. As mentioned before, we are using the FLUG 8.1 software for this analysis. So it is a two-dimensional explicit finite difference numerical program for engineering mechanics computation. So for the overall methodology flow, we started with literature review and information search. We highly relies on the data available online. So based on previous studies and related videos available, because as I mentioned before, we don't have any on-site data. So we then develop the slope geometry model based on the available data online, and then we develop two different model, which is the dry model, which represents unsaturated conditions, and false wet model, which represents the saturated conditions. So we're using the Mohr-Coulomb model. So the values of cohesion, internal friction angle, and tension are important criteria in this model. So using this values, we calculated the FOS with an objective to achieve a range of factor of safety between 1.1 to 1.3. So if we haven't achieved the value, we will modify this cohesion, internal fraction, and tension again until we achieve the required range. So this failure criteria, it generally answers the question of at what value of stress, strain, or energy that the failure will occur. So then we will plot the major principal stress, the vertical stress, the XY displacement, and plasticity and factor of safety plot as our output and presented them as our results. The slide shows the initial slope geometry model developed. So the table shows values obtained from different studies conducted within the vicinity of the study area. So from this table, we summarize the ranges for unsaturated soil materials and its strength properties. So we use these ranges as a basis to pick a starting value for our simulation. So because we wanted the slide to occur similar with the Batangkali landslide, the suggested value for starting the simulation would be applied to the top left of the model, in which it is located left side of the road, highlighted in the red box in the figure. So these three values are crucial for stability, cohesion, angle of internal friction, and tensile strength. So the value of tensile strength is proportional to cohesion, and this means that in a simplified simulation, stability depends on cohesion and on the angle of internal friction. So simulation should be carried out starting with a constant value of one parameter and decreases the values of another until we achieve factor of safety within 1.1 to 1.3. So we will check the weakest values of cohesion and the slope will not slide. So this is an excellent example of how important it is to choose parameters and values of constants for the model, where this figure shows by changing the angle of internal friction by 1 degree just, there is a significant displacement in the model. This is the final slope geometry model and materials criterion for both the dry and false wet model. So the material properties for both models are pretty much the same because logically saturated conditions does not change the type and the soil type and its material properties. However, do note that the values for cohesion, tension, and angle of friction for slided and rooted soils are different between the two models, in which the shear strength properties of soil is reduced to 10 to 12 times in water saturated conditions, which explains the differences between the two models. This slide shows the plot of major principal stress sigma 1 for both model. So the principal stress sigma 1's distribution is similar for both dry and false wet models, where the maximum principal stress value appears in the bottom rock layers, while the minimum principal stress values appears at the upper soil plus the right hand side rock layers. So the model managed to simulate distribution of the major principal stress sigma 1 consistent with the material strength properties. This slide shows the plot of vertical stress sigma 2 for both models. So similarly, the distribution and magnitude of vertical stress sigma 2 for both models are the same, and it is consistent with the soil's material properties. So the maximum value of vertical stress sigma 2 is 1.5 power 6, while the lowest value is 1 power 5. The maximum value occurs at the top part of the bottom rock and the right rock layers, while the minimum value occurs at the upper soil and rooted soil layers. This slide shows the plot of XY displacement and vectors of the displacement for both model. So we can see that from the plot, the displacement is concentrated at the slided soil layers. And the pattern is quite similar for both models, but the magnitude is different. So the range of vector displacement for dry model is within 0 to 5.94, while the vector displacement range for the false wet model is around 0 to 9.78. For both models, the maximum vector displacement is situated at the slided soil, and the simulation results are consistent with the instability situation of soil under water saturated conditions and are able to replicate the Batang Kali landslide. This slide shows the plasticity plot indicator for both models, where significant differences can be observed between the two plots. So the plot shows two failure mechanisms, shear failure and tensile failure. Each plot shows the slided soils are currently on the yield surface, indicating that the zone is at active failure now. And the plot for dry model shows more of a shear failure identified in the middle zone of the model. Both model, so in terms of the magnitude of deformation, the false wet model has a higher magnitude of deformation in both x and y axis. This slide shows the factor of safety plot for dry and false wet model. So the FOS calculated for dry model is 1.05, while the FOS for false wet model is 0.27. So from the FOS value, we know that the dry model is in a stable state, while the false wet model is in unstable state. So the maximum shear strain for both model is concentrated at the same zone, which is the slided zone, but the magnitude for the shear strain is different, where it ranges from 1 to 5 for the dry model and 1.64 to 9 for the false wet model. So from this plot, we are able to get a rough estimation on at which values of shear strength properties that the slope failure will occur. As a conclusion, the comparison of the results of calculation for FOS for both cases from the FLUG program allowed to show that with artificial water saturation, the value of the FOS index decreases to 4 times compared to FOS index in the dry model. So from the simulation, we managed to obtain a rough values of failure criteria in which the point that the landslides will occur. So of course, this is a simplified model, but the model managed to define all the most important geological aspects of the area very well, and it is able to simulate the complex interplay of geological properties and climatic factors that contributes to the slope failure. And that is all from me. Thank you so much for listening, and bye-bye.